which I forgot to do 25 minutes into my last lecture. I was like, no. All right, so what did you guys think of the exam?
Honestly, like for me, I didn't think it was too bad.
Nice.
It was a lot easier, I guess, than what I thought it was going to be.
Okay, so note to self, let me make it harder for the next one. Everybody thank Erin. Yeah, the goal, at least this is just my philosophy, which different professors feel differently, but my goal is never for it to be like a shock and awe and like, what is this? I have never heard of this. The goal is for it to be, we've practiced this. Let's practice it some more to make sure we have some mastery before we move on. So yeah, hopefully there are no surprises. Hopefully a lot of the Excel stuff matched up exactly to what you needed to do during the lab. And hopefully the questions on the exam that were more like content related, they weren't surprises, right? Like median mode, hopefully that was not a surprise. What's a dependent variable? Hopefully not a surprise, right? Like those are things we need to really know moving forward in the semester. So any questions I can help answer, it is not fully graded. I probably have 2 questions left. So I graded by question for every student. So no one test is complete. This way I'm comparing question to question as we go through. It seems like Z tests, there are still some challenges on that. So I just want to make sure before we move forward, if there's any lasting question on that. Although before you ask questions and all that, know that you are not going to get retested on Z scores. I don't know if that matters. If you're like, well, put it behind me, I don't get it, whatever. Or if you're like, no, I feel like I'm so close, but what am I not getting? That was a long explanation. Questions, yes or no? Could have just been what I said. No?
I had trouble with converting the Z-score into a percentage.
Okay.
And like, so I thought I did it right, but I was like, oh, I don't remember doing this exactly, but I know we did.
Yeah. So if we remember, oh, here's Camilla. Let me share the PowerPoint just so I can start doodling. Here, hold on one second. Share the PowerPoint, come on. Can you guys see this? What is happening? Okay. I don't know what's going on. My computer's not wanting to work. Yeah, let's try it again. It's fine. It's fine. It's cool. Let me move it back over here. Oh, that's the issue. It just won't do it at all. Okay, try number 2. Let's have it over here. Sorry, gang. There's always tech issues, right? Okay, here. Do you see it now?
Yeah, it's there.
Can you see my cursor? No? Can you guys see what I'm drawing? Yay! Okay. Hopefully it's a little chat that says yes. Okay, great. Thank you, Liz. So if we think about the curve again, right? And then a Z-score is usually the area. It's either going to be between one point and another, right? Do we remember that? So what is the total percentage under the curve? Do we remember?
Is it like 34 point something?
Oh, okay, what did I just do here? Okay, it's 34. You have, okay, I think I'm hearing what you're doing. Let me be more precise with my question. What is the entire percentage under the entire curve?
Oh, 100.
Yes, very good. 100. Okay. Everybody's on track so far? Okay. Now, if I draw a line right here, I have bisected my curve into 2 parts. What is the percentage on either one?
50.
50. Very good. 50 and 50. Okay. So that makes up, each side together makes 100. So if you are asking to convert a number, right, into a z-score, first off, you need to know the mean. And what is the mean of a z-score?
0.
0, good. Standard deviation on either side is 1, okay? So then if you find a spot like right here, this is the person's score. Remember, we used some example about the SAT writing score. So let's say this was their SAT writing score was right here. You ask what percentile did that student fall into for their writing test? Eyeballing it, there's no good numbers right here, but eyeballing it, what would you say it is?
Like the top 34%.
Ish, maybe a little less than that, because this is my 50% line, right? So I know it's going to be more than 50% because half of the curve is 50, right? So this student is above the mean by a smidge. I was not kind with this example. I could have made it a little clearer, right? So if this is my middle, okay, 0, this is 1, this is -1, and this is their score right on the standard deviation, then you're doing 50 plus, and somebody had the right idea here. What's that? Somebody said it just a second ago. What's the area under the curve between the mean and the first standard deviation?
Like the top 34%.
Yes, so you would add that in. So then you would have to add both of those in, 50 plus 34. And you would get that percentile. Does that make sense? A little bit. Oh my goodness, you got a puppers there, Aaron.
Yeah, my sweet mates and roommate have decided to try to make a return to their so-proclaimed name.
All right, I want to just send a quick message because as we're talking about the exam, I want to make sure that everyone has completed the exam. Did everybody take the exam? Okay. So I will stop talking about it because there's someone that hasn't taken it. Sorry, guys, I'm just direct messaging real fast. Okay, awesome, thank you. All right, so your grades will be posted by next week, and then we can go over it a little bit further as well once we have everything completed. Sound like a plan? Okay, so last week, the last lecture that we did, sorry, I'm trying to catch up now, so there's a ton of chat messages. Okay. The last chapter we did, let's just double check that we're all on the same page here with the syllabus. Nothing like not being on the same page, so it's just good housekeeping. So here we are. Last lecture was chapter 6. We are now moving on to chapter 7. The lab for chapter 7 is on confidence interval. It is very straightforward. We're going to practice a little bit today, and it should be due by next week. I'm saying should because depending on how things are going, I want to give myself that out if necessary. And hold on. My son is in the background. I'm like, don't play video games. Okay, so that is going to be the lab that we do. I may push the quiz back also to the following week as well, because otherwise the quiz is really on just one piece of material and all of a sudden you're getting tested on it and on a lab. I don't know. Does that seems like a double whammy to me? I may be kind and just push that back as well. As we move forward, we've got a few more chapters to cover before the final exam. And there is a significant data analysis that's going to be part of your final exam that I will open up probably a week before the final exam so that you guys have time to work on it. So I just want to introduce it so you guys know about it now. It's going to be a massive data set. When I say massive, there's probably 500 variables, thousands and thousands of participants. Okay, no problem, Hannah. Oh, she's already gone, so her computer died. So thousands of participants, tons of variables, and you will be given instructions to complete certain analyses. So I will tell you, for instance, you need to complete 3 different descriptive analysis, which would mean mean, standard deviation, something like that. And then I'll have you do 2 to 3 inferential analyses, which will be correlation, logistical regression, things we haven't quite covered yet, so don't panic. But you guys are, the part that has been challenging for students before is they're like, there's so many variables, which one do I pick? And that's part of the fun part to me, is that there's tons of variables, so you get to pick whatever sounds interesting. But you also need to be careful to pick variables that are the right type of variable for the analysis. So for instance, if you're doing an analysis that requires quantitative interval ratio items, and you pick a dichotomous or yes, no item, that's going to be a problem. So it's part of the test for you guys to also figure out which variable you should be picking. So I will talk about this further as we go through week by week, but I just want you guys to be prepared that that is something you're going to do outside of class. It's going to be separate from the final exam. And that'll be more like encompassing all the analyses that we've done before, like mean, standard deviation, stuff like that. Questions about that so far? Is that, I mean, I'm just introducing it, so it's little nibbles at a time, but okay. Let me know if there's anything that pops up that you have questions about. Okay, otherwise today we are covering estimation. So let's get to it. So do we ever estimate data? What do we think?
Yes.
In what way?
Maybe to give like a rough estimation of height, just to be very basic. Or like an example I used previously, age, things of that nature.
Absolutely. By definition, what do you hear when you hear estimation?
Like a guess, or like
Yes.
like a almost hypothesis in a way.
You're absolutely
Like you're
correct. Yeah, it is. It's an I don't like to say educated guess, because guess sounds like, well, I just closed my eyes and threw something at the board. Could be anything. It's more than that. We're educated about it. And we'll talk about specifically today confidence intervals. So confidence intervals will mean we think, here, let me draw it out because that's how I visualize it in my head. So we're like, we think it's somewhere in here, right? We know it's not going to be here, but as to whether the answer is going to be this or this or this, we don't know, but we're fairly sure that it's going to be in here. Now, the more accurate you are and the less error you have, the smaller your circle gets, right? And that's obviously the goal, because we want our estimation to be as closely resembling the actual response, okay? So when you hear a confidence interval or that language, or if you hear the answer is this plus or minus 3, right? What comes to mind? Where have you heard them? And maybe you're like, Dr. Wiltil, never. You're about to enlighten me and my mind's going to be blown. Okay, let's go back to November. What happened in November? Oh no. Uh-oh, for real? November.
The election?
Yes, Camilla, woo, for the win. I was like, for a hot minute, I was like, has it been over a year? Am I crazy? Maybe that's why they're not remembering. No, just last November. So when people talk about Gallup polls or poll results, they will often say, we are certain of these scores or these results plus or minus 3, or we believe about 97% of this precinct has been submitted, or we have the results of the election. Is that ringing a bell now? Kind of that language that they've utilized? That's because they don't know 100%, right? The person announcing this information has not looked at every ballot and every result. They are taking the word of each precinct and then adding a little bit of error, because that's human nature. Again, there's going to be some level of error. And so then they can speak with a certain level of certainty as to which candidate they feel is winning based on the amount of error that is presented. Okay, so that's a big introduction to talk about estimation. But the goal for us are going to be to talk about what is estimation, which I've kind of explained already. What are point estimates? What are confidence intervals? What are confidence levels? And then to calculate and interpret confidence intervals for the mean. I'd like to put a little asterisk right here because that is the bulk of what we will do, and that is what your lab is going to focus on. We are also going to tie it in, because the main problem to me with stats, where students are like, oh, it's boring, I hate it, is that it's not tied to real life, right? So we are going to talk about the concept of risk and how that ties in with confidence interval and why confidence intervals are so powerful and necessary. And then the last thing we're going to do is calculate and interpret confidence interval for proportions. But honestly, we're going to focus very little on that, because that's not something I want you guys, it's not going to be on the exam. So I just want the bulk of our time to be on confidence intervals. Okay, that was a long intro. So what is estimation? It is a process where we select a random sample from a population and we use a sample statistic to estimate the population parameter. Okay, I've used several keywords here that we talked about on the exam. So what is a population parameter and what is a sample statistic? What are those? Is it kind of ringing a bell, guys? Uh-oh.
Will sample statistic be like a statistic of not the entire population, but just like a sample of that population?
You got it. So for instance, this could be the mean, right? Which is notated by X bar, or in your textbook in some part, it's Y bar. Dumb. I don't know why they do that. In any graduate book, it's always going to be X bar. So I don't know why your book tries to be different, but in a population parameter, that would be like a mu, right? That is the population mean. So again, estimation is a process by which we take a sample statistic and we try to extrapolate that and estimate a population parameter. For instance, if I were to ask you guys, and think that through here for a minute. Let me see here. What do I want to ask? Oh, this is good. Okay. Think in your head and then put it in the chat. How many hats do you own? I'm not defining what a hat is. You did get to decide if it's like a fedora or like a baseball cap or a toque or whatever. Hat. Think about how many hats you own. Write it in the chat. Love it. Savian, thank you for being a bit different than the rest. Okay, so eyeballing it, I'm seeing 3s and lots of 2s, 6, 1, 4, 20, and 2. Okay, so if I were to do an average real quick, all of you guys pull out your phone or calculator. Let's do an average of that. Okay. So we have a sample. What's our sample size? Oh, wait. Got one more. Oh, one more. Jeez. I'm going too fast, guys. Okay, so what's our sample size? Sample size is just adding how many people are in the class, right?
So I got 12 from that.
I think that's right, right? Or was it 13?
I wrote 14, but I think it's 13.
Oh, 14 was not your answer.
No, I had already given my answer like
Oh, dang
before.
it.
I'm so, yeah, my apologies. That was supposed to be an answer to like.
No, that's fine. Okay, so we've got 13. I'm gonna need to recalculate mine because I added 14 as Hesher's. All right, so what is our mean, the sample mean? So I was at 46 plus 5 divided by 13. 3.92. Anybody else get that? $51. Okay, you guys, I'm gonna need some more active participation here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think it's 11. Can I get some confirmation from someone else? I think there's 11 responses, not 13.
Yeah, I got 4.6 as the mean.
4.63 or something.
Yeah.
Yeah, that's what I got to. 4.636. So we'll say 4.64. Okay, so by taking a sample mean of our class, I could say on average, college students across the world, right? I'm extrapolating to the entire population of college students. They have a mean of around 4.64. Okay. How accurate would it be for me to straight up take the mean from our class of 11 people and generalize it to the entire population? Whoops, sorry. Ah. Would that be accurate?
It'd be fairly inaccurate.
No, it's inaccurate, right? Why is that? Few reasons, right?
Because- Yeah, well, yeah. It's just too small a population. It's going to be compared to like a larger scale. This is a set of college students as opposed to like, the greater population. And we don't know the diversity compared to the diversity of our nation in general.
100%. Perfectly said, Savian. So our sample size is too small. I would dare say it's not representative of the population just based on gender split. I would say it's not representative in terms of just basic ethnic, racial, demographic, right? So, but I can use this number as a platform to estimate the population mean, okay? So I would need to figure out what is the amount of error that is in this calculation, and I would add and subtract it to this number. So then I could say, I'm going to make up numbers here, that the average college student across the world owns between 3.8 and 5.4 hats. I made up these numbers, but this is how I would report it, okay? As a range which takes the point estimate from my sample statistic and I add error to it and I take it away from it. So I get a range. Okay. So that was a long example here about hats, but that gives you an idea. So another example would be the percentage of Americans who identify as environmentalist, according to this study, is 42% as estimated by Gallup. The average level of education in the United States is 13.77 years. And the percentage of Americans who oppose laws requiring transgender people to use the bathroom that correspond to their gender at birth is 39%. I would like to add real quick that this is a study that was done in 2014. We have come a long way since then. But this is just data. This is not the way I feel one way or the other about it, just data, okay? So we have done averages based on that data. And from those points, we can extrapolate to the general population, okay? All right. We can also use sample proportions to estimate population proportion. Same thing with sample means to estimate population means, just like we did a moment ago. And we can also use sample variance to estimate population variance. So how much a data point actually varies within a certain participant pool. We can also mirror that to then the population. So why do we estimate, right? There's many reasons. We've talked about this already, that doing a population or a full census is not cost effective. It's not time effective or efficient, right? And what's the likelihood that you get 100% response rate? Close to zero. Even with the census, you know, they send people out knocking on doors going, you haven't filled out the census. And even by doing that, they still don't get 100% response. So most of the time, we cannot collect data on the entire population. So since we rarely know the actual population parameter, our goal is to have excellent sampling, which is the last thing we talked about, right? Sampling, so that we pick a sample that is representative of the population, and we use statistical inferences to create these estimates to better understand the population parameter, okay? That's the best that we can do because we don't have all the data for an entire population. Okay, does that make sense, kind of the logical leap from estimate? Okay. A point estimate is a sample statistic that's used to estimate the exact value of a population parameter. Okay, it's like my hat idea. So when the Gallup polls report that 42% of Americans identify as environmentalists, they're using a point estimate. Okay, same thing with the average age or average education. They're using an actual point to estimate the population parameter. Okay. The problem with that is that sample statistics vary and there's error, right? So we don't know how accurate they are, just like what we talked about. So we have to use interval estimates because using an exact point estimate is not going to tell the whole story. So instead, using an interval is a preferred method. This way we identify that range where the parameter exists. And then we'll talk about in terms of how much certainty we feel that that parameter is within that range. So a confidence interval is a range of values that's defined by the confidence level within which the population parameter is estimated to fall. So that is often referred to as the margin of error. So education levels, the point estimate was 13.77 according to that Gallup poll, but the education level is probably between 12 to 14. That's a better range, right? It's found somewhere in there rather than saying, nope, 13.77, right? It's like saying the average US family has 2.17 kid, right? It's some random statistic like that. Well, I don't know who's having that 0.1 baby. I have all full babies. They all are a full point, right? So instead, you could say between 2 and 3 children, okay? The confidence level is the likelihood expressed by a percentage that the specific interval will contain the population parameter, okay? So the most common one is 90, 95, or 99%, but honestly, in almost everything, you're gonna hear 95% confidence interval. Occasionally you'll have 90%, and very rarely you'll have 99%. That's like, I am dead set. I know exactly. I'm 99% confident that it's going to be in here. So for a 95% confidence interval, we have a 5% margin of error, or a 5% chance of not containing the population parameter. Okay, so it's the radius of a confidence interval. This is key because we never know for sure, right? We're estimating. So we recognize there's error, but we need at some point to be like, okay, well, yes, this is probably not the most accurate number, but I feel 95% confident that it's going to be somewhere in this range. Okay. And then we can go with that, especially in the social sciences, right? Like and in fact, even experimental studies utilize confidence interval, right? They say with a certain degree of certainty that a test will be sensitive, right? What's an example that comes to mind where they use confidence interval for a specific experimental drug, maybe, or test? Think of what's going on for the last year.
The vaccine.
The vaccine, or even COVID testing, right? They'll say, yeah, we'll take this test and it is X amount effective, plus or minus, blah, blah, right? Like we're 95% confident that it's going to be effective at finding the, sorry, my dog ran right into our post of our deck. I don't know how he doesn't like bonk his head here. So that's how we use it then in real life. Okay, so we can use estimations to lead to inferences. So you could take a sample of Americans, which you're trying to approximate the entire population, right, of Americans. So you use some sort of sampling procedure here to get your sample. That subset, then you calculate the sample mean and the standard deviation, and you then circle back to the population. You can infer the parameter for that specific population. Okay, so see how we did that for this. It was the Gallup poll. We took a sample of Americans, asked them, how many years of education did you complete? We got to this average, 13.77. Now we can infer that most Americans have between 12 and 14 years of education. Okay, so every time you use a sample statistic, you go through that exact same cycle. Yeah, I just explained that. Done. All right. The population distribution. This is important because a population, the way it varies, may differ from your sample, especially if you didn't do a good job sampling. Okay. So we want to know about the variation in the larger group that we want to know about. We want to know about that distribution. Okay. And it's going to be important to know about the distribution of our sample to see if they mirror one another. Then a normal distribution is the one whose mean and standard deviation are unbiased of the parameter and allows one to infer the parameter from the statistic. Again, the goal is most populations are going to be normally distributed because there's such a large number. When we sample a subset of that population, we are trying to estimate and match up that same distribution as the population, right? So we don't get skewed data. So sampling, accurate sampling techniques is key for this. Okay. You guys remember central limit theorem? We're right back at it. Okay. So even if a population distribution is skewed, we know that the sampling distribution of the mean is normally distributed. Okay. That's just that it all reverts back to the central limit theorem. As the sample size gets larger, as I just talked about, the mean of the sample distribution becomes equal to the population mean. And as the sample size gets larger, the standard error decreases, okay? Because the more and more people, again, like we talked about, our example of hats with 11 people responding, tons of error, right? Because one person says 20, the other person, let's say, said 0, don't own a single hat. Well, okay, we've got outliers then, right? But the greater the number in your sample, the more you will approximate a normal curve. That is what the central limit theorem tells us. Now, we should know researchers do not typically perform repeated measures of the same, repeated samples of the same population. They use their knowledge of theoretical sampling distribution to then utilize it and create confidence intervals. Again, this is an issue of efficiency, right? I could say, well, I want to know all about college students, so I'm going to sample 80 colleges and 100 students from each. Whew. Okay, well, now you're getting real close to that population. But remember, we had a graph a few weeks ago where it talked about diminishing returns, right? You can keep on adding to your sample size, but at one point, it's not going to reduce the error anymore, or not in a significant way. So finding an appropriate sample size and knowing what the error term is going to be, and then creating a confidence level around it, that's key. So the confidence level then is the likelihood expressed as a percentage or a probability, usually 95%, that a specified interval will contain the population parameter. So I'm 95% confident that most Americans have between 12 and 14 years of education. Okay. So the 95% confidence level, another way to think about it is that there's a 0.95 probability that a specified interval does contain the population mean, okay? 0.95 probability that the population parameter is within that interval. So in other words, there's 5 chances out of 100 that the interval does not contain the population mean. So this is key again. It is an estimate. It is possible that there is error. That's just how it goes, okay? But the more we can reduce that error, the more confident we feel in our interval. So same thing, if you have a 99% confidence level, there's 1 chance out of 100 that the interval does not contain the population mean. Frankly, how do you guys feel about this level of risk? 5% chance, 1% chance that it's not contained? Let me put it in real.
I think, oh, I'm sorry.
No, you go,
I
Diane.
think that a 5% like chance of like error not being in there like isn't like that bad. Like I wouldn't be so concerned as to like having a 99% confidence level.
Mhm.
If that makes any sense, or if that's
Yeah.
what you're looking for.
Yeah, totally. Now, let me put it in kind of a real world scenario. You work at a state hospital and you are in charge of releasing or kind of creating a report that states that somebody is ready to be released from the state hospital after they have committed murder, let's say. And you give them this risk assessment, it's a test, and it gives them a percentage of chance of recidivism. What is the risk that they will reoffend in a violent way, okay? And you get 5% chance. Are you good with that? Do you release them? Do we feel better if there's only 1% chance?
I think we'd feel better if there was 1% chance.
Yeah.
Of
Recidivism. Yeah, reoffense.
recidivism.
Yeah. So this is where we can tie it into real life, right? So if we know that a test will tell us with some level of certainty, I mean, 95% confident, that means there's still 5% chance they'll still do it, right? So this is that risk balance that we need to consider. And so when you look at those numbers, it's like, what are the odds that when you decide to go bungee jump when you're in New Zealand, back when the world travels again, what are the odds that the bungee cord will snap? And maybe you're the kind of individual who would research that right before they step on the platform. And then you calculate the risk. You're like, well, no, I feel pretty good about that. I don't know what that risk is. I'm just making stuff up here. Same thing, like I'll go to Hawaii and swim in the ocean. What's the risk of me, getting eaten by a shark, right? So there's risk involved. And then we can talk about like, what's the likelihood that'll happen? But again, we base that on what we've seen. We have a sample of when it's occurred, and we're extrapolating it to what we think will happen to us in everyday life. And obviously with that, there's always a certain amount of error. Okay, does that kind of make sense? Kind of bringing it home a little bit? Okay. I like to talk about stats all night, but I think I'm gonna get a lot of these faces. All right, so confidence interval. First off, we always use the sample statistics. So we start with sample means. That's the point estimate of the population mean. Your sample standard deviation, again, is the point estimate of the population standard deviation. And your standard error of the mean makes it possible to state that the probability that an interval around that point estimate contains the actual population mean. Okay, so that standard error is what will create that interval. So here's what it looks like. So if you want to construct that estimate, you figure out your mean, right? And then you figure out what is your error and you add that to the mean and subtract it from it. And that becomes your confidence interval. And then we say the population parameter falls somewhere around here. We feel fairly 95% or 99% confident that the population parameter falls here. Now, standard error of the mean is important because that's what we're adding to the mean. So it is the standard deviation of a sampling distribution of means, okay, which is kind of complicated. So how much does our sampling mean differ from the actual population mean? This is different than standard deviation of a sample of individual score. So the standard error of the sampling distribution is shown as this. So it is the standard deviation of your sample mean over the standard deviation of your population divided by the square root of the sample size. Now, problems with that? Do we often know the population standard deviation? No, we're doing approximations, right? So what we do know based on the law, and again, we've talked about this before, is that a total of 68% of all random sample means fall within plus or minus one standard deviation of the true population mean. So you guys remember us doing that on the chart? Right, like we did something like this. And then this was, oh boy, my drawings are not great tonight, gang. So this is -1 plus 1, whoops. So this is, oh boy, this is bad. 68%, right? Is this ringing a bell for everyone? Okay. 95% of all random sample means fall within 1.96 standard error of the true population mean. Okay, this is going to be something you always need to remember. Okay. And 99% falls within 2.58. You will not need to know about 99%. We don't use that very often, but 95%, that is our gold standard, okay? 1.96 standard error of the true population mean. Okay. So since the standard error is not usually known, you work with the estimated standard error. So you go kind of the same path. You're doing the sample statistics first. So this is the sample distribution of the mean, sample of our standard deviation of your sample divided by the square root of your sample size. And here's what it looks like. So your confidence interval is your sample mean, right? Plus or minus Z for 1/2 of the acceptable error. And this is your estimated standard error. You're multiplying those two here. I realize this is just a lot of jargon. We're going to get to an example and it's going to make more sense. Bottom line, we've done this already with hats, right? So you would plug in your mean for your sample and you would add and take away the product of these two, which is the Z-score of 1/2 of the acceptable error times the estimated standard error. Okay. So first things first, you need your sample mean. Next, you need to calculate the standard error of the mean. Then you decide on the level of confidence and find the corresponding Z value. You calculate the confidence interval and you interpret the result. Easy as pie, 5 easy steps, right? Okay. So what does that look like? So let's say you know there's 15,000 commuters on campus, right? Probably a lot more than that this year, right? Because are dorms open again? Yes, they are.
Yeah.
Now, 15,000 commuters, that is a lot of people to be asking and surveying. You can't test them all, so we randomly sample 500 students and ask them how many hours per week do you commute? We get the mean of their scores, and let's say their score is 7.5 hours per week that they commute. We have a large sample size, so we doubt our sample is going to deviate a whole lot from the population mean based on the central limit theorem. So we want to know that the interval that would capture our true population mean is in that interval. All right. So the way we do that is we calculate the standard error of the mean based on our sample standard deviation. Okay. So the standard deviation we're told is 1.5. It's not calculated here, but this is what it is. And you would divide it by the square root of your sample size. So here it is. This is now the standard error of the mean based on the sample standard deviation. Next up, we pick a confidence level corresponding to the z-value. Number one, I said, like, remember this number. This is the number we're always going to use, right? So what is the z-value we're going to use? .96, right? Everybody's seeing that? I'm not being too obtuse here. This is what it is, 1.96. Hint, hint, you'll want to know that for quizzes and exams. All right, so we decide on a 95% confidence interval. So the z-value is 1.96. So now what I'm doing is I know that this is my sample mean, and I take away the product of these two, which this is my z-score, 1.96, and this is my standard error based on the standard deviation of the sample, 0.07. Okay, so this gets me 0.14. I add it and take it away, so it gives me a range of 7.36 to 7.64. So the takeaway message here would be, on average, Aquinas students commute between 7.36 to 7.64 hours per week. Okay, and I feel 95% confident that that is accurate for the Aquinas population of commuters. Questions about these calculations? What you got for me?
How did you get the 0.07?
Great question, Lainey. All right, so let's go back over here. So first, we were given this value here was just given to us as the standard deviation, okay? And then I divided it by the square root of my sample, which is 500. So in a problem, I would give you this value. And obviously, I would give you the sample size. I would give you the mean. I would give you the mean, yes. So that's how you got 0.07. So then bringing it back, then we plug it in right here. Other questions? Okay. So now let's say we want to increase our confidence level from 95 to 99%. So it means we're less willing to draw the wrong conclusion. Okay, we really want to know, like, I want to be 99% accurate. So if we reduce our risk of being wrong, this is kind of interesting, and this is a common mistake. To reduce our risk, we need a wider range. Okay, to reduce our risk and feel more certain that the population parameter is in there, we need to widen our range. Why is that?
Because there's less error.
Exactly. The wider my range, the less error there is. Because now if I'm like, yeah, I think average Americans have between 10th grade, 10 years of education and 18 years of education. 100%. There's maybe zero error in that somewhere it falls right in there, that the population mean would be in there. Because now I've just made my range really, really big. The smaller my range, the greater the chance that I might miss my population parameter. Okay. So by reducing our risk, the interval becomes less precise. So now where did I get this number? 2.58. Okay, remember this is my Z-score. Let's go back a few slides. Whoops, a few slides right here. 99% tells me it's 2.58. So I plug that in. It's still the same standard error, right? So it's still 0.07. So now my range is 7.32 to 7.68. Does that make sense? Okay. All right. So again, this is a sample mean. It gives you an idea of the width of your interval. See how this interval is larger than this one, right? So less error, but less precise and wider interval. Okay. So the idea of risk is that we are trying to minimize that as much as possible, right? We want to have as little risk as possible so that we feel certain it falls in there. So if we are in fact wrong, right, we fall in that risk category. If the specified interval does not contain the true population, then we have taken that risk and we've fallen into the error pit, so to speak. So to reduce the risk, we increase the confidence interval. Okay, so notice here, these wider bands, right? If you make it bigger and a wider range, it's going to include it. All right. So again, this is all repeating the same idea, but I want to make sure we've got it. So we are 95% sure that the mean in terms of number of hours that students commute is between 7.36 hours to 7.64. But there remains a 5% chance that the population mean is actually somewhere outside of that range. There's 5% chance, okay? 99% confidence interval, same thing. So we're 99% sure that the mean falls between 7.32 and 7.68, but there remains a 1% chance that the population mean falls outside of that. Make sense? Okay. So when we look at the width of a confidence interval, we can think also of sample size. So the larger the samples leads to smaller standard error. That kind of makes sense, right? Like we talked about, a sample of 11 in our class, lots of error, right? But a sample of 1,000, a lot less error, okay? So in sampling distributions that are more clustered around the population mean, there's definitely less error. Okay. My dogs are barking like crazy. Can you guys hear them? Let me just quickly tell them to come in. Come on. Okay, well, I actually realized that that's not even my dog. That's the neighbor's dog. That's obnoxious. Sorry, can't do much about that. Okay. Same with the standard deviation. Smaller sample standard deviations result in smaller, more precise confidence intervals, right? So the less variation there is in a sample, the more precise it's going to be. All right, so this is another example. That's kind of a fun one. So in the GSS, and this is actually the study that you guys will get a ton of data from for the final project. 1,001 people were sampled, and they were asked how many hours a day Americans spend watching TV. Okay, they discovered from those 1,001 participants that the average is 2.94 with a standard deviation of 2.6. Let's pause here. First off, does that seem low or high compared to your experience or how much TV perhaps you watch? What do you think?
I'd say that's probably low.
Low. See, I wonder if now, because I think again, this was the 2014 General Social Survey. I feel like now you should swap out TV watching for like screens, time on screens. Because I think so many people watch stuff on their phone or their tablets, maybe not even a TV. Or is that just, am I incorrect about that? What do you guys think?
No, I was kind of wondering the same thing. Like, does that like count as like watching like an actual like thing on TV, or like what is actually going on TV?
Right. Do you guys get that? I have an iPhone and it tells me this week your X amount percentage screen down is up or down. Do you guys get that? I get so angry because I feel very judged by my own phone. And I'm like, I was using the maps. If I'm using the maps, my screen is on. So you think I'm like watching, but that's not the same as me scrolling Facebook. There should be a difference. As some programmer needs to figure that out because it's very upsetting to me. I could probably disable that. Actually, now I'm thinking that about it's causing me grief. Just turn that off. What is something else that you notice from these numbers? The average is 2.94 and the standard deviation is 2.6.
The standard deviation is really big.
Very good. Okay, now who said that? Was that Hannah?
It was me.
Yeah, very good. So what does that tell us about our sample?
They're not very similar.
Exactly. There's a lot of variability, okay? Which means it's possible somebody watches 13 hours of TV a day and someone else might watch 0, right? Okay, so we may have some outliers, but just regardless, there's high level of variability within our sample, okay? So now we're going to use the sample standard deviation as an estimate of the population standard deviation. Okay, this is the same formula we did earlier. So we have a given standard deviation, 2.6. Sorry, that looks weird. And we divide it by our sample size, which is 1,001, which gives us a standard error of the sample of 0.08. Okay. So now we're going to go through the same steps that we did earlier with the other example. So let me turn off my chat here. Oops, and it's not working. There we go. So if I want a 95% confidence interval, I'm going to plug in my values, which is my sample mean plus or minus the Z times the standard, that's not right. Actually, that is right. Standard deviation of the mean, standard error. Okay. So 2.94, how did we get this?
That's the average amount of hours that people spend watching TV.
Exactly. That is the mean number of hours, right? That was given to us. Plus or minus, now I know it's 95%, so I need to use 1.96, right? That is my Z-score for the 95% confidence interval. And then I know my standard error is 0.08 because I just calculated it. So now I multiply these two and the product of it is 0.16. I subtracted from the mean and I added to the mean, which gives me this range of 2.78 to 3.10. Okay. So I am 95% confident that the average American watches between 2.78 to 3.10 hours of TV per day, right? Day or week? Day. Week. I don't know what I'm thinking. Obviously, it's got to be day. Okay. Does that make sense? Questions on how I got those numbers? Because this is how fancy we're going to get here with the math. It doesn't get any harder than that. So if there's something here that's not making sense, I want to make sure I can address it. Okay, I'm going to keep on trucking. All right, So this is a 95% confidence interval and width for a mean number of hours per day for 3 different sample sizes, okay? Now note, this is where we were, 1,001, right? Which led to this confidence interval, this width, which is just the difference between the two. I feel like that should be the, yeah, that's the mean. No, that's not the mean. That's the standard deviation. Sorry, standard deviation. Okay. So note here what they did. They got all of the values to figure out how much of a difference it would make if we lowered our sample size a lot or increased our sample size by a lot. So the first thing you need to do is you need to actually calculate the standard error, right? So this was our standard deviation of the mean, 2.60. We have it here. Our sample size is now 1987, which gives us a standard error of the mean of 0.06. Now look at my interval, okay? 2.82 to 3.06. It is reduced in width, meaning I've become, even though I'm still keeping 95% confidence, my interval has shrunk because as my sample size goes up, I'm feeling more confident that the population parameter is going to be in that range. Now, what happens to the interval width over here when I reduce my sample size to 150? What do you notice?
It's a lot greater.
It's a lot greater, right? So, I mean, that is a very wide confidence interval. So yeah, I'm saying I'm 95% confident that it's in this interval, but it's a much larger interval. So that's why I can be 95% confident, okay? So it's less accurate. All right. Now, what do we do if we want to calculate the 99% confidence interval for it? Okay, so we would take, again, my standard deviation divided by the square root of my sample size, which again, this is 1986, so we've got the same standard error of the mean. Okay, this was for 1.96, so now how do we do it with 99%? How does this formula change?
The z-score changes to 2.58 is, sorry, I think I have that.
No, you're right. So it becomes 2.58. And then what do you multiply it by?
By the standard error.
Exactly. So it's 0.06. Okay. Now we know what it is. Well, no, we don't. We know what it is for 95%. So you guys take a moment and calculate that. Okay. Are you guys adding it all up? Whoops. Okay, what's the first part of the interval?
I got a 15.48 for the 258 times 0.06.
So this is 2.58. So I just want to make sure you got that because your numbers are right. No, you're right. So it's 0.1546. Very good. And now we do plus or minus our mean, which is 2.94. So what is the lower part of the interval?
2.79.
2.79. And what's the upper part of my interval?
3.09.
Very good. Okay, so this is my 99% confidence interval for a population, for a sample of 1987. Does that make sense how we did that? Thank you. Okay. So here's the relationship between our sample size and our confidence interval width, okay? If the width is fairly wide, right, we've got a larger, a larger interval for our value, okay? Then we end up having a confidence interval that is not very precise, okay? It's gonna be very wide. As the interval width gets smaller, we become more and more precise. Okay. However, gains get increasingly modest after a sample size of around 2000. That is the law of diminishing return. You can keep on sampling, but you're not going to get infinitely less error. It's not going to be that much better, right? At one point, you got to call it quits and go, that's good enough. Right? That interval is pretty good to show me what I'm looking for. Does that make sense? Okay. Here's another example. So 95% confidence intervals for the mean income of Puerto Ricans, Mexicans, and Cubans. This is another example in your text. Let's see if there's additional information I want to tell you about the year. I think it was published in 2014. Okay. There's nearly 55 million people of Hispanic or Latino ethnicity in the United States in 2014. Mexican origin Hispanics comprise the single largest group of Hispanics in the country, but the origins of the Hispanic population have diversified with the addition of immigrants from other Latin American nations and Puerto Rico. During the past few decades, studies have noted the discrepancy in earnings between these groups. So in this study, they argued that Mexicans, Puerto Ricans, and Cubans varied markedly in socioeconomic characteristics because of differences in the timing and circumstances of their immigration to the United States. Okay, so then what we did is we figured out what was the mean income for each of those groups and created a confidence interval. There's additional data that's described here in your textbook, but for now, that's pretty good. Okay. So again, I would utilize this formula to calculate a confidence interval. I would need to know my sample mean, right? And I need to know also, in order to get my standard error, I need to know the sample size. So you can see the sample size is here for each of these groups, okay? And then we were able to get the sample mean for each of them right here. And then we created a 95% confidence interval for each of those groups. So you see here 16,289 to 16,785, these values over here, and so on and so forth. Okay. So that's how we could compare then groups. So it's one thing to compare means alone, right? If I'm just comparing these right here, that might be significant. Comparing means is doing a t-test, right? That might be important. But if I look at the actual interval, then I can estimate what is my population parameter for each of those groups. And there's value in that as well. Okay, now, a dog begging to get him. Come on, inside, dog boy. Okay. Now this is the part that I want you guys to recognize. This is like, we need to know about this, but it's mostly just for your own edification. So confidence intervals for proportion. We can estimate the standard error of a proportion based on the central limit theorem. So we would use here our proportion. So you can see here, the mean is right here. The mean of the proportion is equal to the population proportion. That's the nomenclature for it. And with a standard error of the proportion. This is not going to make a whole lot of sense. Let me just go to the next slide. Okay. Because the standard error of proportion is generally not known, we work with the estimated standard error. So this is the sample proportion This is 1 minus that proportion divided by your sample size. That gives you your standard error of proportion. So let's do an example. So in the example I gave earlier in the Gallup survey, they identified that 42% were environmentalists, okay? So here, let's go back over here. Note this is the proportion times 1 minus the proportion. The proportion is 0.42 times 1 minus the proportion, right? So this is the inverse. And then based on this, I then divide it by the sample size and I take the square root of the whole thing. So I divide it by 1,019, which tells me this is my sample, and take the square root of the whole thing. So my standard error of the proportion is 0.02. Okay. For the rest of it, you just plug and chug, just like the others. Okay. So consider that, again, there's 2 factors to meet the assumption of normality within a sampling distribution of proportion. The sample size and the sample proportion are the 2, right? So when P and 1 minus P are about 50%, a sample size of at least 50 is sufficient. Meaning, if you've got a group or a proportion that's like 10%, that's going to be a greater problem. Okay, you're going to have a group that's going to be much higher than near that 50%. If you have that, a more skewed proportion, you need a larger sample to meet the assumption of normality. Okay. The purpose of this exercise, here's the way you plug that in. So P is the observed sample proportion, right? Plus or minus the product of the Z-score times the estimated standard error of the proportion. So very similar to what we just did for the mean. So you do the same 5 steps. Measure your proportion, calculate the standard error of the proportion, decide on your level of confidence and the corresponding Z-value, calculate your confidence interval, and then interpret your results. That's the way you would go about it. Okay. So for this particular example, if I want a 95% confidence interval that 42% of Americans are environmentalists, I would do, this is my proportion, 0.42, plus or minus the product of my Z-score, which is 1.96, times my standard error of the proportion, which is 0.02, which gives me a range or confidence interval of 0.38 to 0.46. Or I am 95% confident that 38 to 46% of Americans consider themselves environmentalists. Okay, that's what it would look like in terms of a proportion. Does that make sense? Okay. Let's practice it with 39% this time. Okay, you guys work on this calculation. Okay, are we adding up those numbers? All right, so what goes in here? What is P?
.39.
0.39. Okay, multiplied by 1 minus 0.39 divided by, what's my N?
1049.
Yep, 1,049. Okay, so what did you guys get as your standard error of the proportion?
I got 0.015.
Everybody else get that? 0.015? Looking up in the chat. Okay, good. Good. I like it when other people verify my math too, so thank you. Okay, now what do we do next? This doggy of mine, can you guys hear him? He's like, oh, Mom, come on. I want to go back outside. I've been inside for 5 minutes. Let me back out. All right, so what do I do next?
You plug in like everything for your equation. So you like your proportion would be 0.39 and your z would be 1.96 because it's a 95% interval, and then you would plug in standard error.
You got it. Okay, so I just plug in all of my values and then I end up with the range. Okay, which let's do that real fast. Okay. That is hopefully everybody got this. Is that what people got? .36 to 0.42, right? Did you guys all get that? Or no?
I did.
Okay, good.
Yeah.
I need some validation here, so I'm not feeling 100%. I want to make sure I'm not leading you guys astray. So again, if you were to put into words, what are the results? What does it mean?
That we're 95% confident that the proportion of Americans that oppose laws requiring like transgender people to use bathrooms is between 0.36 and 0.42.
Exactly. Or you could even switch that to say it's between 36 to 42%. Yeah, excellent. Does the concept of confidence interval, does that make sense to everyone? Okay. It's not challenging. It does require some math, but I think it's pretty manageable, right? Again, on an exam, you will be asked to do this, but this is as complex as the math will get. Okay. I think understanding the relationship between how wide an interval is and then the level of error that you have, or the preciseness, I think that's important to grasp because oftentimes people flip that around. Okay, so again, you will have less error the wider your interval is, because it's almost like, what are the chances that if I had a bow and arrow that I would hit the target if the target is this big versus if it's this big, right? The bigger the target, the greater the likelihood I'm going to hit it, right? So same thing. The larger your interval, the greater the likelihood your population parameter is going to be in there. Okay, does that make sense? Okay. These are the common terms that you guys need to review to make sure that you have, that you know and are familiar with. Okay, so let's do this. And then I want to go and talk about the lab real fast. Where are we? Okay, so here's the confidence interval lab. And this is where you would submit it. So here's what it looks like. Oh, that's weird. Okay, hold on. I think it doesn't like it when maybe it's open already. No. Here it is. Computers are so weird, you guys. Why do you work now and a second ago you didn't work? Come on. Okay. So here's what you're going to be doing. The question is there a difference in the mean number of hours that kids watch TV per week based on their parents' marital status? You'll need to complete a 95% confidence interval for each group. And lastly, what conclusions can you draw from this? Okay. So what is the first thing you need to do?
Find the mean.
Find the mean. Okay. So I'm just going to write a few notes here. So step 1, you need to find the mean. What is step 2? Find the
Standard error.
well, we're going to figure out standard deviation first, right? Because I didn't give that to you. Okay. Third, find the standard error of, of the mean. Fourth, figure out the z-score for 95% confidence interval. Hint, hint, what is it? Always the same, 1.96. 5, plug in values. Okay, so you will do it first for unmarried parents. Do you guys remember how to calculate a mean? Easy peasy, lemon squeezy, right? Remember how to calculate a standard deviation? There's a nice formula, equal standard deviation of a sample. Okay, you do that. It's gonna get angry because it says, I don't have any, oh, hold on. Standard deviation of a sample. And I'm gonna select all of these guys, right? This, whoops. I get too excited here. Okay. Did it still throw me an error? Okay, you get the idea. I don't know what I'm doing wrong here. Maybe I have to do it at the bottom. But you need to figure out the standard deviation, and then you're gonna plug in the same values from the formulas that we just did, and you're gonna do that twice. And then you're gonna end up with an average or confidence interval for each of them, and you're gonna be able to compare them. Okay, and then the last thing is, what conclusions can you draw from this? I want you guys to be able to say, it appears that marital status does play a role in how much TV kids watch, or it appears it has no impact. Does that make sense? Pretty straightforward? Okay, that is the assignment. So you will complete that. Oh, I'm getting, okay, yep. So you will calculate those, and then on Course Connect, make sure you submit it by next week. And then that's the lab. We are going to postpone the quiz. I think that just makes more sense to wait till we have a little bit more content. Are you going to play some music for us there, Aaron? Is that a trombone?
Yeah. Just been kind of, everyone's gone. I'm here all alone. Gotta find something to do to stay occupied while attention.
Nice. Okay, any questions about this? Does it make sense?
Are
Everybody's
those,
feeling,
like
Go ahead.
bullet points that you just made, will those still be on the Excel document when we do it?
no, but it will
Okay.
be on this video,
Okay, perfect.
and I'm sure in all of your brains. Yeah, it's the same thing. I created the same list that's actually on the lecture that says
Okay.
exactly where to go. Yeah.
Perfect. Thank you.
No problem. Okay, that's what I've got for you guys tonight. Enjoy the lab. It's a fun one. And I'll make sure to submit it by next week, and then we'll go from there. Okay, you guys, have a great night.
Thanks,
Thank
Professor.
you.
Have a
Have
great
good
week.
night.
Thank you. Bye.